Hello, my name is Lucas Rodrigues. I'm very happy that you chose to watch this video presentation. This work was done with the aid of all this group in the Photonic Materials Laboratory of the University of São Paulo, in the Chemistry Institute. And this is my email if you want to comment or to collaborate or anything you want to talk with me. So I'm presenting a little bit about our work with SrS sulfide doped with divalent europium that present this very nice red-orange persistent luminescence color, how we can prepare this material very fast using microwave, and what we can understand of these materials using techniques like Zanet's EPR and microscopy. So first, persistent luminescence is a phenomenon where you can store light in the materials. So persistent luminescence materials are light storage materials. They are like batteries, but you're not storing electricity, you're storing light. So if you have one watch like this, you must have noticed that in the dark you can see the pointers. This is persistent luminescence materials. Some roads nowadays use this to guide you through the night, and maybe in the future we can use this as bioimaging in diagnostics. But nowadays these are mainly in rats, mouses, for studies to understand drug deliveries and things like that. So how does it work? If you see here, when I put some hot water on this plate with persistent luminescence, you see that the green light is brighter after I pour some hot water. And this happens because the charge trapping followed by room temperature thermostimulated luminescence. This is the phenomenon. So it's a thermostimulated luminescence. This is not phosphorescence. So when I put some hot water, I give it more thermal energy and it releases the energy faster. So you can look that is releasing more photons per time, and that's why it's brighter. This is a phenomenon well known for the last 25 years, but its origins goes back to the Chinese Empire. But it's very efficient for some ions like divalent europium, chromium, manganese and other, especially when the mechanism is related to electron trapping, as I'm showing next. And normally with divalent europium you get blue or green color. And how does the mechanism works? So first you have an excitation that leads europium to plus to the excited for F5D state. This state is somehow overlapped with the conduction band, and this electron is trapped in some defect. When this electron is trapped, it can stay trapped for a very long time, depending on the energy difference between this defect and the conduction band. If this defect is very deep, it can stay for years, like the materials you use in dosimeters. But when you give thermal energy, this electron goes back to the 4F5D state, and then you have the emission that can happen for a long time, depending on the concentration of defects you have, and of course the position related to the conduction band. So this phenomenon is dependent on the band gap energy, on the energy level position, and the defect position. In this work we are going to focus on the defects. So why did we choose SrS sulfide? So to get red persistent luminescence materials with divalent europium ions, you have two options. The first option is to increase the crystal field of europium 2+. When you increase the crystal field, the split of the 5D will lead to lower energy emissions. But to get divalent europium with red emission color, you must have very strong crystal field. The other option is that you can decrease the barycenter of the 4F5D state. And this happens with the increasing of covalence due to the neophyloxetic effect. So when you decrease 4F5D, you can get red emission even with lower or weaker crystal field. That's the case of strontium sulfide, a very covalent host but with very weak crystal field. The other option that leads us to choose strontium sulfide is that this host has strontium, that's a hard acid, and sulfide, that's a soft base. If you remember Pearson's theory on acids and bases of Lewis, materials that are made with hard acids and hard bases, or soft acids and soft bases, are very stable. But when you mix hard acid with soft base, you have weaker bonds. So strontium sulfide is a host with weak bond. Defect formation is related to the breaking bonds. So it's an endothermic process that you must give energy to the system to break these bonds and form defects. So the weaker bonds of strontium sulfide leads to high defect concentration in this material. That's why it's so nice for persistent luminescence. So how can we get this material prepared? The conventional synthesis includes inductive heating at temperatures from 1000 to 1200 degrees Celsius, using gases like carbon monoxide, hydrogen or hydrogen sulfide to reduce sulfate to sulfide and trivalent europium to divalent europium. This takes normally 1 to 4 hours of calcination with a total synthesis time of around 12 hours, including heating, calcinating and cooling. This is a very high energy consumption. We developed a synthesis using microwave, so we use actually the dielectric heating. The temperature can achieve from 11 to 1300 degrees. The atmosphere is carbon monoxide that's generated in situ due to the use of carbon. That's the susceptor for microwave and also the generator of CO. This takes normally 20 to 40 minutes of calcination with a total synthesis time of 3 hours from heating, calcinating and cooling. So it's a very low energy consumption. This method works very nicely. You can see that we tried 2 cycles of heating of 20 minutes. The first cycle, still we have some strontium sulfate peaks. And after the second cycle of heating, we have only strontium sulfide peaks in the XRD. So, if we look at the microscopies, we can see that the sintering took place and we have very, very big particles. So, it's not a nanoparticle synthesis. Does it work to reduce sulfur or europium? Yes. So when we look at sulfur K-edge in the soft X-ray beamline, we can see that these peaks are related to sulfur in the sulfide oxidation state. So we could reduce sulfate to sulfide. However, when we look to europium, we look that the majority of europium in this material, it's in the trivalent state. When we look in the derivative, we have more information. We can see that we have some divalent europium, but the majority is in the trivalent state. Well, the material is very efficient. So what's happening? Why can't I see divalent state as majority? Well, can it be the synthesis? Yes, it could be the synthesis. But as we are going to look later, the material can photooxidize under light. When you excite europium 2 plus to europium to the 4F5D and then you trap this electron, you're actually photooxidizing europium 2 plus to europium 3 plus. And this material presents very efficient X-ray excited optical luminescence and persistent luminescence under X-ray irradiation. So we can excite this material with X-ray close to the strontium edge, to the sulfur edge, and we always obtain the europium 2 plus emission profile, as we are going to see later under UV, is the same emission profile, a broad band with maximum at 620 nanometers. So X-ray can induce persistent luminescence in this material. You can have this very nice red emission and persistent luminescence happening after you stop the X-ray irradiation, before or after the edge, in this case in the sulfur K edge. You can still get very long persistent luminescence under X-ray. So the majority of trivalent europium in the Xanes can be because you are photooxidizing divalent europium. How can we prove this? Well, we can use electron paramagnetic resonance or EPR spectroscopy because it's a non-oxidizing technique. Europium has two EPR active isotopes, the 151 and the 153, and they are more or less in the same proportion. Europium nuclear spin is 5 halves, so we should see 6 peak split per isotope in the EPR spectroscopy. This is the experimental EPR that we measured, and this is the calculated using the G value of 1.9995. And more important, this calculation considered that we don't have pure strontium sulfide, because we are looking at least 13 peaks, as you can see here. So either we have some impurity or some extra site, but strontium sulfide is cubic and has only one strontium site. Europium is occupying strontium site, so there is only one. And we don't have the formation of europium clusters, otherwise we would see in the EPR. So we must have some impurity. It can be strontium sulfide from the precursor, or some impurity due to the moisture reacting to strontium sulfide. Anyhow, this is not very strong impurity signal, and we can calculate including this impurity, so we can see that we have divalent europium in our system. When we irradiate this material with 405 laser, we observe a decrease on the EPR signal, and using the double integration of this curve, we can conclude that at least half of the europium 2 plus disappeared under 405 light. So what's happening? Well, if we remember the mechanism, after the excitation, the electron is trapped in the defects, and in this process, europium 2 plus is oxidized to europium 3 plus. So when we excite with 405 nanometers laser, we are photooxidizing europium 2 plus to europium 3 plus, and at least 50% of this europium 2 plus is excited with this laser. is a very interesting signal, proving that during the mechanism, europium 2+ is really photooxidized to europium 3+ during trapping. So let's try to understand a little bit more this mechanism for this material. So the first thing is to look at the band gap energy. We can see this very nice excitation band with different codopants, and using the derivative we see that the band gap is close to 4.5 electron volts as it's expected from the literature. Here you still see the 4F5D excitation. And when you look at the luminescence of this material, when you have pure europium 2+, you can get a very nice and broad band at 620. That gives the red color for europium 2+ persistent luminescence. Its excitation is in the green and blue region, so it's very nice to excite with visible light. The very weak crystal field makes possible this green light excitation to red emission. And this is the same with all different codopants. You only observe europium 2+. Here we put cerium as a comparison. With cerium you have some green emission, but when you have europium and cerium you only get red emission. So all the other codopants actually transfer the energy or does not impact europium 2+ emission. So this is a very red emission with any other codopant. And when you look at the persistent luminescence, you see this very long persistent luminescence in the orange-red color. When you have only europium 2+, you have around 13 minutes of persistent luminescence, and this is measured in candela, so you can see when you stop observing it. Well, actually this is the human eye limit, but it's not optimized for a red color. Anyhow, for only europium you should observe this persistent luminescence for 13 minutes. When you codope with some trivalent rare earth, this increased to 60 minutes, except for cerium that increased to 40 minutes. This can be related to the very low, very short persistent luminescence time with cerium 3+. Anyhow, independent on the codopant, except for cerium, the persistent luminescence time does not change a lot, except when you put more codopant from 1% to 2% of codopants, then you have 75 minutes of persistent luminescence. This is not a common thing to observe. If you look at literature, you see that most of the compounds that are formed with europium 2+ and a different codopant, the persistent luminescence time is very different among the codopants. Mainly because in the majority of these materials, the codopant acts as an electron trap, and the energy position of the divalent codopant is very important. However, here we are looking that independent on the codopant, you don't change the persistent luminescence time, indicating that a different mechanism is happening here when you add the codopant. So to understand the defects, we can make some calculations using some statistical thermodynamics, and we can observe the molar fraction of the defects based on the energy formation of these defects. So for the Schottky pair, strontium and sulfide vacancies, at room temperature you should have no defect per mole, 10 to the minus 59 defect per mole. But when you go to 1500 Kelvin, more or less the synthesis temperature, you should get 10 to the 12th defect per mole. This is a very high concentration of defects. But you can ask, when I cool it down, it should go back to very low defect concentration. No, because this cooling is very fast, especially if you are using microwave synthesis. So the advantage of the microwave synthesis is that you cool very fast the system and you freeze the defects. So we should still have a very, very large concentration of defect in this material. Well, the Frankel concentration is not very high. You should not see any interstitial sulfide. The concentration is very low, and maybe you should have some strontium sulfide interstitially, but anyhow, short pair defects are the most important for these materials. You can look at the thermoluminescence glow curve of this material co-doped with samarium, and it presents two bands, one close to 100 Celsius degrees, the other at 350, and all the codopants present very similar thermoluminescence glow curves. So the codopant is not changing the type of defect form. So the defect might only be acting, the codopant might only be acting as a defect formation via charge compensation, since you're substituting divalent strontium to trivalent rare earth. To look if the rare earth, the divalent, could act as an electron trap, we calculated the energy level position, and you see that the majority of the codopants has its ground state energy of the divalent codopant inside the conduction band, and that's why they are not acting as electron traps. So actually the rare earth is only increasing the defect concentration via charge compensation, and this defect concentration is already high due to the weak bond between sulfide and strontium. So mainly the mechanism is related to the blue or even UV light excitation. It's a cubic system, so you have europium in the excited state with Eg and T2G, and after the excitation this electron is trapped in these defects, and when it returns it emits the red color. So concluding, hard soft S-base pairs are good candidates for a persistent luminescence host, since they have low energy of bonds. EPR proved to be a good technique to measure europium 2+ photooxidation in the persistent luminescence materials. The rare earth codopants can sometimes act only as charge compensating defects, as we observed here, and since this material is a hard acid soft base, is very reactive, especially to moisture, some surface treatment is needed to protect these moisture sensitive materials. I would like to thank you, the agents that financed this project, the University of São Paulo, the Synchrotron Laboratory of Brazil, and also the Turun Yliopisto from Finland that provided us some measurements. And I would like to thank all my group. And if you want to know a little bit more what we are doing, you can follow our Facebook page, or you can download the paper of this presentation. Thank you very much, and I'm open for questions via email.